Hello and welcome. This is SFU Math 152. My name is Brenda Davison. This is section 6.2 on volumes. So we're going to learn how to use the definite integral to compute a volume. So just before we get started, let's just take a look at some of the classic volume formulas that you probably recall. So here's the volume of a right circular cylinder with where the base has a radius r and the height is h. So the volume, I'm going to point to this, this portion here is the area of the base, and then that is the height of the cylinder. So it's the area of the base times the height. And you can handle all cylinders like this. So I could have a cylinder that, I don't know, that looked like this. Can I possibly make that same shape again up here? Nope, I can't. But let's try again. That's really bad. Let me just try to draw the same kind of shape. Sort of shape like that. Okay, assume those two shapes are the same, and I made a cylinder out in this manner here. I would be able to calculate the volume of this cylinder if I could calculate the area of the base. I would just take the area of this base and multiply by the height. So we can handle all cylinders in this manner here. Okay, the cone, the volume of the cone. We're going to see how where that 1/3 comes from. So the volume of the cone is 1/3 pi r squared h. We have the volume of a sphere, 4/3 pi r cubed, and we have a square pyramid, 1/3 the base squared times the height. So we see this 1/3 coming out a couple of times. So how do we prove these formulas, or how do we come up with them? And in fact, how exactly are we going to be defining a volume? So let's just take a look at that and then see how we're going to go about doing this. So there is the volume of a general cylinder with cross-sectional area A. There is a cylinder, and then we've got this cross-sectional area A. This means if I cut the cylinder anywhere along perpendicular here to the base. Well, I guess it's parallel to the base, perpendicular to the height. I will, when I look down, when I cut the cylinder like that, I look down, I see the same shape. It doesn't matter where I cut it, at the base or near the top, anywhere where I cut it, I see that this is the what the cross section looks like when I look down on the top of the cylinder. Okay, and if I can figure out the area of that, then I will have the volume of the thing by multiplying by that height. And one sort of to say this, if you take a look here at this nice little organized stack of coins, the volume of those coins is unchanged if I sort of move it like this. So the volume actually could look quite a little bit different in this version over here, but that's actually the same volume. So if the cross-sectional pieces are rearranged, it doesn't matter. It still is going to give us the same volume. So this is a principle called Cavaliere's principle. So this is a mathematician. He lived quite a long time ago now, 1598 to 1647. Okay, so those are the same volume. That's what this is telling us. Same volume. Okay. In general, the volume of a solid is defined using integrals. Okay, so what are we going to do? We're going to use an approximation method, and then we're going to take a limit, just like we did when we were trying to find area. So for an arbitrary solid, we approximate the volume using cylinders, which we know how to find the volume of, and then we allow the number of cylinders to become infinite. And then we get the exact volume when that happens. Okay, so let's just take a look at a graphic to represent that process. So say we wish to find the volume of this solid here. This basically looks like a vase lying on its side. Okay, we want to know what is the volume of that. We imagine just dividing it up in the first instance into 4 pieces like that. And then we sort of pick some sort of, maybe in the middle or something like that, we pick some sort of height, and then we say, okay, that's fine. we pick some height, we pick some point here, and maybe the midpoint or something, and we use that, and then we make a cylinder right there. And then we say that the volume of that port will be that cylinder, and then we pick some other one here, and we make a cylinder here, etc. That's the diagram here. So we've chosen, I guess in this one, it's been the left-hand point like that. The point's over here on the left like that, and we then just assume that it's a flat in that little area, and then we would approximate first this volume by the volume of these 4 cylinders, which we can easily compute. And then if we think that's not good enough, which it looks like it isn't, we then approximate with 10 cylinders, and then we would approximate by 15 cylinders, and you can see what's happening. The more cylinders I use, the smaller the little cylinders get, and the more closely this approximates the total area. And then what we do is we let the number of cylinders become infinite. Okay, so we can do that in general. Here's a picture. We have a volume that we're trying to calculate we have a solid S, which we're trying to calculate the volume of, and we imagine the ith cylinder that is sitting in there, and then we take the base of that cylinder and we multiply by the height of that cylinder, and then we let the number of cylinders become infinite. So one cylinder, we just look at what is one cylinder. One cylinder. So the volume of that little slice of the cylinder, S sub I, that is approximately the area of the base of that cylinder times the height. So this is the base, and then this is the height, and that is this formula here, volume of SI. That is this right here, this volume here, the volume of the ith sliver of the total solid S. Okay, so then we add up all n of the cylinders. So then we imagine we have, okay, so for n cylinders, we simply add them all up. So this will be the volume for the whole solid, then will be the sum of all n cylinders. And this is actually not quite an equal sign yet, because we are taking a finite number of cylinders, and the area is like that, and then the height is like that. Okay, then we make the number of cylinders large. We make the number of cylinders large, and then we get the exact volume in the limit. So we take the limit as n goes to infinity of the sum of I equals 1 to n of the area of the base times the height. That is the definition of the volume. So this is the definition of volume. Okay, and then I just looking at this from sort of a mathematical perspective, that is the limit of a Riemann sum. So it's a definite integral. This is the limit of a Riemann sum. Therefore, well, that tells us, that implies, usually use that for implies it is a definite integral. So we're going to be able to calculate volumes using the definite integral, just as we could calculate areas using the definite integral. So here's the definition of volume. Let S be a solid that lies between x equals a and x equals b if the cross-sectional area of S in the plane px through x and perpendicular to the x-axis is a of x, where a is a continuous function. Then the volume S is the integral from a to b of a of x dx. Okay. Right, let's put this into an example. Hopefully things will become clearer Okay, so we're going to see in this course two types of volumes, I suppose. Volumes, we can sort of a more arbitrary one like this, and then we're also going to see special types of volumes, which are volumes of revolution. Okay, that's coming. I just want to alert you to the fact that this is not a volume of revolution. You cannot take something and revolve it around the axis and get a shape like this. So just for when that comes, don't confuse that the coming discussion with this discussion. This is just to show how we can calculate the area of a square pyramid, the formula for an area of a square pyramid, by looking at integrating all of these little squares as x goes from 0 to h. So that's what we're going to try to do. We're going to integrate along the x-axis from 0 to h. And so we're just imagining putting in these little tiny squares here and adding them all together. So I've got the square here and the square here. I'm adding up all these little squares. They're actually yeah. So it's a square. The base is a square, and then I'm imagining just a very small little height, delta x, and then that becomes quite infinitesimal as the number of squares increases. Okay, so that's what I'm going to be doing here. Let us try that out. Sort of lost my pagination here. Okay, I'm not sure what happened there. Let's see. Let's just leave that. Okay, so we're going to integrate along the x-axis. So we're integrating in this way here, going from 0 to h. That's the solid starts at 0 and the solid ends at h. Okay, let's just take a look at the endpoints. A of x equals the area of the square at position x. So this is the area of the square. This is, I should say here, maybe like the perpendicular. So this is, you can see that the area when x is 0, the area of the square, that would be right here at the origin, is 0. And then you can see the area of the square when x is equal to h. What is that? Well, a of h is b squared, because this distance right here is b. So when x is h, the area of this n square here is b squared. Okay, so now what we have to be able to do is say, okay, now I'm going to look at an arbitrary square. That's the one I've got here in a sort of slightly pinkish color. Let me just put it in, darken it in here. This one right here. This is at an arbitrary, I'm thinking of an arbitrary x along here. And once I have that x, can I figure out what the area of that shaded square is? That's my task right now, because once I can do that, then I can just simply add up all of these squares. So that's my idea. So I need to figure out what this value here is, y, right? Because here, let me just erase this and show you here, this value y. Okay, so that y is a function of x, and that y is the length of the square, and so the area there is y squared. Okay, so I know that a of x is y squared once I've labeled that side y. Now I need to understand how to calculate y as a function of x. Okay, so this is a geometry problem. So y is in fact x times b over h. And that is by similar triangles. Okay, so you might want to draw yourself and play around a little bit until you can see how that works. But we've got a similar triangle situation where we've got something here, something that's looking like this, where this would, let's see, let me not do this wrong. This would be b over 2. this would be h along here. This is x here. And then we're asking for this height right here. Okay, so you can use similar triangles and figure out that that height, which I put here, which is really y over 2, and you can then use that to figure out that y is x times b over h. So that means that a of x being y squared is x squared times b squared over h squared. Now it's a simple matter for me to calculate the volume. The volume is simply the integral from 0 to h of the area, b squared over h squared times x squared, times the little incremental width of the this little guy here. I'm just going to draw a picture. I've got that. I've got that. That is my by base, and I've got I'm thinking of a little tiny increment so that I have something that looks like this. Okay. Like that. Okay, so this is my, when I draw it like this, it's really a delta x, but I'm thinking of it as getting very, very small. That's the dx, and then the area of the square is the b squared over h squared times x squared, and I'm going to add those all up. Well, the volume is, let's compute this integral. The volume then is b squared over h squared times 1/3 x cubed evaluated at 0 and h, and that is 1/3 b squared over h squared times h cubed minus 0, and that simplifies to this 1/3 b squared h. So now you see where the 1/3 comes from. So it looks like a bit of a mystery, but it's not. It shows up here during the integration. So that's how I would find the formula for the volume of a pyramid whose base is square. Okay. Now, we're mostly going to focus in this course on finding solids of revolution. That one that we just did was not a solid of revolution. The solids of revolution, this is a special type of solid. Okay, so it's a subset of all the types of solids. Not all solids are solids of revolution, but ones that we form by rotating a line around, rotating a function value around a specific line R. So we're going to see what happens here. So I'm imagining taking the blue line here, which I could have as a function that could look something like this. For example, f of x equals 2. That would be a potential for this function, and I rotate it around the x-axis. So I take this guy and I rotate it around, like I take it and I rotate it around this x-axis, and I look at what happens. So I rotate it around. I get a cylinder. Okay, so rotating a horizontal line like that around the x-axis, I get a cylinder. You'll notice that because I've rotated something around the x-axis, the cross-section, so if I were to cut this anywhere along here and take a look at the cross-section, it is a circle. Okay, that is a circle. Let me do the next one. Maybe pause yourself, think, okay, what shape's going to take? I take this blue line here on this one and I rotate around the x-axis. What shape do I end up with? That is, so I rotate this around and I'm going to get something that looks like this, and it's going to be now three-dimensional as it sweeps out through space, going around like that, like that. It is a cone. Okay, so it's a cone. All right, it's a cone, but notice again that because it's a volume of revolution, that the cross-sectional area there is a circle. And do the same thing with the next one. I rotate this one around this way, so I'm going to get something that looks like this, but it sweeps out. It comes like out of the page and then goes back in, and so I see like that, is a sphere. If I take a semicircle like that and I rotate it around the x-axis, it comes out of the page, sweeps out around the axis back, and I get a sphere. So here I got the cone, here I get the sphere. Again, the cross sections are circular. That is always the case on a volume of revolution. That you will notice was not the case here. The cross sections here, right there, the cross section was a square. So this is not a volume of revolution. That's not a circle. Okay, the final example here, I'm going to revolve this guy around, and that's going to then something go like this, like that, and it's going to look like that. So it's going to be basically looking like the vase that we had in the first example. I'm not totally happy with I'm not totally happy with the way I drew that there. Let me just do a better job. And I'm even going to dash this to try to show that it goes in behind. Similarly, why don't I dash this to show that it's behind? And then if I would take any cross section here, the same thing's going to happen. I take a cross section here like that. That cross section right there is a circle. So we're going to try to get a procedure down for finding the volumes of these solids, and by rotating a region around the x-axis, and then we'll be able to do it around the y-axis, and maybe even any other straight lines that we want to. Okay, so let's go through the first example of this. We would idea here: find the volume of the solid obtained by rotating the region bounded by the curves y equals sine x, x equals pi by 2, and y equals 0 about the x-axis. Now let's get a picture of what this thing's going to look like. And we'll draw our axes. We know we're going from y equals 0. So y equals 0 is this line right here, y equals 0. That's the x-axis. We want to line x equals pi by 2. Well, that's pi by 2. And then we want the sine function. And the sine function goes up like that between 0 and pi by 2. So this line, this y equals sine x, that is that line right there. Okay, now we're going to take that and rotate it about the x-axis. So I'm going to draw, as best I can, a mirror image of the upper line there, and just extend that down. And then just to sort of give it the proper 3D look to it, I'm going to add these lines like this for visualization. So I'm imagining like this, looking like that, and maybe I'll even draw another one of the cross sections in here like that. So were I to cut it at this point right here, I would see a circular cross section, this circular cross section right here. So I'm asking, what is the volume of this thing, which basically looks like a solid bowl tipped on its side. Okay, so my cross sections here, I imagine I'm looking at a typical cross section here, this value here being x, some value between 0 and pi by 2. I imagine, maybe I'll put this in another color. I imagine just a very thin little cylinder here, looking like that. So then I'm going to calculate the volume of that cylinder, and then I am going to add up all of those cylinders going in this direction here from 0 to pi by 2. Okay, so what is the area of my cross section? It is a circle, right? Because all of the cross sections are circular, so the area of my cross section is the area of a circle. So now I'm talking about finding the area here of the base of this little cylinder. So I'm looking at the area of that cross section, and the radius is this y value right here. Right? I'm at this x coordinate here, and then the radius will be y. But y is equal to sine x. So the radius of the cross section at this point here at x is y, and y is sine x. So the area here of that cross section, the area is pi times y squared. That's pi r squared, where the radius is r is y, and I know that y is sine x, so that becomes pi sine squared x. Okay, that is the area of the base of the approximating cylinder. So I've now figured that out. What I want to do now is add up all of those. So the volume of this thing is going to be the sum, the integral from 0 to pi by 2, right, of the area of the base of the approximating cylinder multiplied by the little minuscule little height. So we have now solved the problem. We can now compute the area of this bowl formed by taking the first, the sine function between 0 and pi by 2 and rotating that about the x-axis and then asking what volume do we have there. All you have to be able to do is compute this volume. So which I'm going to write by, I'm going to just factor that pi out of there. I really have to, I'm seeing clearly that what I need to be able to do is integrate sine squared. And that's when I'm going to need the half angle formula. We've seen we needed the cosquared half angle formula before. So sorry, the cosine half angle formula. So let us get the half angle formula involving the sine squared. That is this one here, 1 minus cos 2x over 2. These guys are very handy for being able to simplify some of the integrals when you just see something that looks like this, sine squared. It's just to recall, the other one looks like this. Okay, so those two trig identities are highly useful. So we're going to substitute in here for the sine squared, and sine squared is 1/2 minus 1/2 cos 2x dx. Now this is a simple integral. We can integrate this by inspection and evaluate at the endpoints, and our problem is solved. So just for you to be aware, actually, it is going to be the case, likely going to be the case anyhow, frequently on tests, I will not ask you to go possibly any further than this. It will be just like set up the integral to find the volume. Set up the integral to find the surface area. We haven't seen how to do that yet, or set up the integral to find the thing. Because really, I mean, we can separately test, can you evaluate integrals? But the interesting part and the more difficult part, and the part that your computer can't do so easily, is understanding how to go from the problem to the integral that you want to evaluate. So we are going to focus on that, and you can expect that for some examination questions you'll be asked to set up an integral but not bother evaluating it. Certainly if it says don't set up but do not evaluate, then don't spend exam time evaluating it to a number, okay? Because we won't be giving anything for that. We're just going to make sure that you can get the proper integral. So here we are. We're going to just quickly finish this one. It's 1/2 minus 1/2 cos x. So this is a straightforward integral. That is, the volume is then going to be pi times 1/2 x evaluated at 0 and pi by 2 minus 1/4 sine 2x evaluated at 0 and pi by 2, like that. I do the arithmetic now and I find out, and again you should check those steps, I got pi squared by 4. So the volume of that bowl is pi squared by 4. Okay, let's do another one. We are now going to rotate about the y-axis. Okay, last one we rotated about the x-axis. We're going to rotate about the y-axis. So let's see what happens. We've got a curve. We've got a region bounded by some curves, and then we're going to rotate that about the y-axis. I'm going to draw a picture of what this looks like. We have the curve y equals square root x. That looks like that. We have the curve y equals 1. So I'm going to come across here. This is going to then be 1, like that. So that's y equals 1, continuing like that. And then we have the other one, x equals 0. So that's that. So now we've identified the region there. There's the region. That is the region bounded by those 3 curves. Now we're going to take that and we are going to rotate it around the y-axis. Okay, so that means that the shape will look like this, and it will be, do a bit better of a job. I'm trying to make a mirror of that curve there, like that. Okay, and the cross section will be, circular when so this, I'm going to show you where the circular cross section they are here. So I've rotated around the y-axis. So when I cut perpendicular to the y-axis, I will always see circles here. Okay, so I'm cutting it. I'm thinking of cutting it and looking down. And then if I was just to look at the top here, I would, on my 2-dimensional plane, I usually try to draw this something like this, right, to give a sense of what's going on. So that's the top. It's a circle when you look at the top. So it's a sort of a type of vase that wouldn't stand up, right? It's sitting on a point and it flares up, and it's wouldn't balance very well at all. Okay, so what we are thinking then is that we have little cylinders piled in here, and now they're piled in a different way. So here's the base of one of my cylinders, and then it has a little bit of height, and I'm going to add up all of those cylinders. We're going to start calling these things sometimes discs, sometimes washers. In fact, we're going to typically call them washers because we're going to see soon that we could in fact have a hole in them. Okay, so these washers are perpendicular to the y-axis, which is what we rotated around. Okay, so what is the volume here? I have to go integrating up on the y-axis because I'm adding cylinders on the y that are perpendicular to the y-axis. So it looks like this. The volume goes from 0 to 1. So I'm integrating in this direction. So it's dy. And I need to know what is the cross-sectional area of my washer here. What is the cross-sectional area of that? And that is going to be some function of y. So the radius is x, right? This, if I pick some value here, y, then I go out here, I see that is x. So my radius is x. So my area as a function of, I want it as a function of y, but off the top I can see that it's pi times x squared. And then I am integrating with respect to y. I need to establish the area as a function of y, and I have a relationship between x and y, and I know that y is equal to the square root of x, which means that y squared is equal to x. So here I replace x with y squared, and then it's still squared. Okay, that gives me that my area as a function of y, the area of my circle right here, is going to be pi times y to the 4. Okay, now I can, now my problem is very close to being solved. The volume of this shape is the integral from 0 to 1 of pi y to the 4 dy, and that is 1/5 y to the 5, let's not forget the pi, times pi evaluated at 0 and 1, and that is, let's see, pi by 5. Okay, so you cannot, you notice that if I'm going to use the washer, what I'm going to call the washer method now, I'm just going to roll back here. I used the washer method when it was revolving around the x-axis. I integrated with respect to x. I used the washer method when it revolved around the y-axis, and I integrated with respect to y. You cannot, once somebody has told you in the problem that you're going to rotate around the x or the y-axis, that forces the direction of integration. You don't have any choice about that. So you're sometimes going to have to go by y. Okay. So let us take a slightly more complicated example now. We'll take an example where we want to find the volume of the solid obtained by irritating the region R. So it's going to tell us how to make R, enclosed by the curves y equals x and y equals x cubed in the first quadrant, about the line y equals 3. And we're going to do that first, and then we'll revolve it about the line x equals 2. So now we're not even revolving about the axes. So let's just get a picture of what the region looks like that we're going to be rotating. So here it is. This is it's enclosed by two curves, y equals x. So that is y equals x, and then y equals x cubed. That is y equals x cubed. So there indeed is the, and we're in the first quadrant. So that's the region we're going to rotate. And first we're going to rotate it about the line y equals 3. Draw another picture over here, what that looks like. Here is the x-axis. Here is the line 1, 2, 3. Okay, and here is my region. So this is going to be 1. This is 1, 2, and this is y equals 3. That's what I'm gonna be rotating about the y equals 3 axis. And I've got this region, and let me just make this one here, that this region looks like this. Looks like this. It's there it is. Okay, straight on the top there and curved on the bottom. That's just a smaller version of this guy right here. And it rotates around. So where is it going to end up? Let's think. This is 1, 2, 3, 4, 5, 6. So this point right here is 2 away from here. So it's going to have to be 1, 2 away from here. So this point will be here. The flat line will be here like that, and the curved line will be here like that. Okay, there it is there. Okay, and we've rotated it about that axis, and so the base here, the cross sections are circular like always, and so we have a shape that looks like this. Okay, cross sections are circular because it's a volume of revolution, and there is the shape there. It is a bowl, and it is not a solid bowl like the previous example. Okay, so now the cross section is it is circular, but it's not a solid circle. So the cross section, this is why we call this the washer method, because washers are things that that you put on a screw before screwing it in, that stops your screw from loosening, and they basically look like this. Okay, that's what a washer looks like. And so you can see that in this case that our cross section here, it indeed looks exactly like that. So we have a cross section here, and it's like that. And it's in fact, if I were to look down at this blue cross section, it's going to be, in fact, it is in fact a washer, and the way I've drawn it, it's washer is going to be like that. It's mostly open in the center, and then it's got a rim around it. So what we're going to want to do is add up all of those washers. We are going to, you'll notice the washers are oriented this way here, like this. So that means we have to integrate in this direction here. Okay. So how are we going to do this? What is the cross-sectional area? So my first thing is to identify the cross-sectional area. Okay, what does that look like? Well, it is pi r squared. So what is the outer radius? So what I'm doing now is I've got basically two radii. I'm going to identify the area of that outer circle, and then I'm going to subtract the area of the inner circle on my typical washer that is at distance here x. So I've got some distance over here x, and I'm looking, what is the cross-sectional area? A of x as a function of x. Okay, so that is, I'm looking then, what is my inner radius? So let's just think about my inner radius here. My inner radius is 3 minus x. Okay, because why? Let's think about why is that. Because y equals x, and the inner radius is to right here, to this inner line. That is the line y equals x, and we are we're about the line 3, so that radius is going to be 3 minus whatever x value that is, because that is whatever y is. You can test this easily by looking at what would be the radius right here when x is 0. You should get 3. And what's the radius right here when x is 1? You should get the radius should be 2. So that works. Say the outer radius. The outer radius is 3 minus x squared. Okay. Y equals x squared is this curve right here. Y equals x squared. So I have an inner and outer radius on my washer, and I then can calculate what the cross-sectional area A of x is. A of x is pi r squared, pi times the outer radius squared, minus pi times the inner radius squared. Okay, the problem is now basically solved. So the volume of my solid is going to be I'm going to put the pi on the outside, factoring that pi out, the integral from 0 to 1. That's because I'm going this way here, and it's going from 0 to 1. And it's going to be the area, the cross-sectional area. That is pi times that, multiplied by the infinitesimal height of each one of those cylinders, and then I'm adding them all together. Looking like that. Okay, problem solved. Let me just put in a couple of the extra steps here. That is going to be 0 to 1. I expand 3 minus x cubed squared, and I get 9 minus 6x cubed plus x to the 6. And then I subtract and I expand that one there, and I get 9 minus 6x plus x squared. And I'm still, that's the integrand there. And I can maybe simplify a little bit, combining some like terms, and I maybe reorganize plus x to the 6 plus 6x minus x squared dx. Okay, so now I have a very simple integral. It's just a power rule on each one of those functions, and then I have to evaluate at 0 and 1. And so I went through that whole procedure, and what number did I get? Do I see this number here? Huh. No, I don't see the number here. I just see it detailed out in this manner here. Let me write this down. So you check me and see if this is the area. I didn't simplify. I got this. Okay. So that is the volume, which actually speaks to something that's also going to happen in the exams, and that is we're going to leave our answers in quote-unquote calculator-ready form, which with something like this, I guess you could do a little bit more by hand, but for the most part, you know, something that looks like this. That's calculator-ready form. You're not going to be simplifying that. There's no need to simplify it. That is a number. So if that's the answer, you just leave it like that. That's what we call calculator ready form. Okay, I'm going to now set up the integral to do the same question when I rotate about the line x equals 2. I'm going to rotate the same region about the line x equals 2. And I'm going to set up the integral. And then once I've set up the integral, then I'm just going to give you the answer. I'm going to encourage you to evaluate the integral and check the answer. But the conceptual part is setting up the integral. And we're just going to have to go down past this, get a little bit of space here so that we can do that. Okay, so around x equals 2. This is the same region. So let me redraw the picture. It's going to look like this. I'm going to make this line here x equals 2. And that means this would be x equals 1, and then this will be the y-axis here. Okay, that's where x equals 0, y, and then that's the x-axis there. So this is 1, 2, 3, and 4. And I've got that same region, which we saw, so between 1 and 1 here, like that, 1. And just like that. Okay, and now I'm rotating it around this axis here. So what happens? Let's see. This distance here is 1. So I'm going to go over here 1, and it's going to. I'm mirroring that region. It's a little bit far. I'm mirroring that region. The region across the x equals 2 axis. So that will look like this. That's 4. It'll look like this. Okay, so the shape that I now get, it's a slightly unusual looking shape maybe. It looks like this. So it's a bowl, and it's got washers for cross sections, and the sides of the bowl sort of increase as it goes down. It's empty on the inside, and the inside is curved like this, and the outside has straight sides. Okay, so I'm going to just draw a typical washer. A typical washer is going to be right here. We'll just pick one right here. It's going to look like this. From there, okay, and then the inner radius of this washer is right there. So we've got this little washer in here, like this. So the inner radius is to there, and then the outer radius is way around here, like that. Okay, and we're going to imagine stacking all of those things up. Which way are we going to have to integrate? Our washers are piled up vertically. We are going to have to integrate dy. Okay, so we're going to be integrating this way. Our washers are piled up this way, and our little width of the washer there, that's a delta y. It's in the y direction. So this is our direction of integration. Okay. So now we have to identify what that cross-sectional area is, and then we're good to go. Okay, so what is the cross-sectional area? Let's just get a list of what our functions are. In fact, our functions are, I have to look back to get the functions that we use to make the region. Let me just write those down onto here so we see what we're doing. This one here is this curve. I'm not happy with that. Let me just get another color. I'm going to this one here is that is y equals x cubed, and then this one here is y equals x. Okay, so we are about this line y equals 2. So I'm saying, given a value of y right here, right? I'm going to be given a value of y. what is this radius right here? So this is some value of y. What is our inner radius? And then after that, what is our outer radius? So this is going to be the, let us do it this way. Outer radius. What is that radius? For some given value of y, that radius is, let's see, it's how I want to do this. 2 minus f of x. Does that sound good? I think so. I mean, that's sort of thinking of it on this side. So this distance would be 2, which is this distance, minus the f of x, which is that distance. So the outer radius is 2 minus f of x, where f of x is the, I guess that's the outer function. In fact, this is, they're both like this. So the inner radius is the same, actually. 2 minus f of x, but the function is going to be different. And so the inner radius, the function is this one here, y equals x cubed. Y equals x cubed. That is for the inner radius. The function is y equals x cubed, which means that x equals the x cubed root of y. Okay, so the inner radius then is, as a function of y, is 2 minus the cube root of y. The outer radius is 2 minus y, because that function is y equals x. These are separate. So I get the inner and outer radius of my washer, and then my cross-sectional area will be pi times the outer radius squared minus pi times the inner radius squared. Okay, so now I can easily set up my integral. The volume is equal to, and I'm integrating with respect to y. I'm going, starting at here, y equals 0, and I'm headed up here to y equals 1. So the volume is pi times the integral from 0 to 1 of the ay, well, I've already got part of the ay there, 2 minus y squared minus 2 minus y to the 1/3 squared dy. Okay, problem solved. You have to, I mean, you expand, you integrate, you evaluate, but that's the mechanics of it. It's easy. It's just a power function, no trouble. So you can do this integral. Please do it. Check me. Check me for sure. I am prone to making mistakes, particularly when I have to talk, write, and think at the same time. It seems worse than walking, chewing bubblegum, and patting my stomach at the same time. So it's easy for me to make small errors. So please check. And so the volume here, when I did this, I got 11 pi over 15. Okay, so we can find that volume. Okay, we're going to do one final thing. We're going to develop the formula for finding the area of a torus. And we have a torus here with, you can see what we're calling an inner radius r. This means something that's slightly different. That means this radius right here. And then we have what we're calling an outer radius r, which is how far from the center of the torus to the inside of the thing. So we've got this bagel or donut shaped thing, which we more sophisticatedly call a torus. And we understand the size of this circle here, because we know that it's that little circle has area pi little r squared, and then we know how far that little circle is from the center of this three-dimensional shape, which is right there. Okay, so how are we thinking about this? We are thinking about taking a circle like this, And I'm just going to have another line drawn over here like that. We're thinking of taking this circle right here like that. And we are thinking of just drawing that line there for now. And we're thinking of taking it. This is we're going to set this up on the y-axis. And we're thinking of rotating the circle around the y-axis like this. So we end up over here with another circle like that. That line being that line here. And we go around like that. And I mean, I've sort of now drawn, you know, half the bagel if I were to cut it along a line right here. Okay. I cut down with my my cleaver and then flip the bagel up a little bit, and that's what I'm looking at right there. And this distance here is r. Okay, that's the distance r, and then this distance here is little r. Okay, so we're thinking, okay, so now it becomes a geometry problem to identify what is the outer radius and what is the inner radius. So I'm looking at this and I see where capital R is there, and I'm like, okay, hang on. So I've got the outer radius is going to be R plus something, right? Here's the outer radius right here. So that's going to be R. I'm going to call that r plus x, and then the inner radius, in fact, is this one right here, that one right there. So that is going to be r minus x. Okay, and where are we going to integrate from minus little r to plus r. So we're going to integrate across here. Pause, think about the geometry of this situation. It's not the hard part is thinking about exactly where everything is and keeping track. So I'm going to draw a little circle here. This is an enlarged view of this circle here. We've got something coming down through here. We've got a midpoint here. We've got that little radius r there. We've got that horizontal line in there. We've got this distance here, y, and this distance here, x. Okay, we want to know what is x. So we've got x squared plus y squared is r squared on that little circle. So x is the square root of r squared minus y squared. Okay, so that means we can establish our outer and inner radius. So I've calculated this value x, that is this value x. Okay, so my outer radius is r plus x, and that is r plus the square root of r squared minus y squared, and the inner radius is r minus x, and that is r minus r squared minus y squared. Okay, so now I want to integrate the volume of my torus. I want to integrate from minus r to r of the outer radius squared minus the inner radius squared. And I integrate with respect to y. Okay. Let's proceed to do this. So I'm gonna skip some algebra steps of expanding and simplifying, and please go ahead and do those. So there's some algebra steps missing here, and then I'm going to get this down to something that looks like this, like that. So that why don't I even make it hopefully clearer by moving everything outside the integral that doesn't depend upon y. And I'm left with this thing here, r squared minus y squared dy. Okay, this looks hard. We've set up the integral, but this does not look so easy to evaluate. We will see how to do this using a trigonometric substitution, but we actually don't know how to do that. However, all is not lost. Let us just take a careful look at this and then think, what is this actually? This is we saw this tactic in one of the first couple of lectures. This is actually the area of half of a circle of radius r. So now we can actually evaluate that without integrating. So we need to recognize this, like we did before, as the area of 1/2 of a circle of radius r. Okay, so we know what that is. That is, well, it would be pi r squared, but it's half, so that's pi r squared over 2. So then we can combine that with the previous information, that is 4 pi r times 1/2 pi r squared, and we can then simplify and we get 2 pi squared r squared r. So now we have a formula for the volume of the torus. Volume torus equals 2 pi squared r squared r. So calculus is really useful in allowing us to find the volume formulas for a variety of shapes. You just need to, ones that you can set up as a volume of revolution, as long as you follow the procedure and whatnot, it is straightforward then to find what the formulas are. Okay, that is all for finding volumes here via the washer method. We are soon to see another method of finding volume using a method of cylindrical shells. See you then. Bye-bye.